Good. Hi, welcome to OPGW Engineering 401. Today we're going to be discussing lightning, the theory and the practice of working with lightning in your OPGW. I'm Mike Riddle, Executive Vice President here at NCAB America. And on behalf of NCAB America, we're glad that you could participate with us today. So we got some things to go over first. So this is a RCEP compliant webinar, which means you can get continuing education credits. This particular one is worth 1.25 credit hours. So the way that works is that after the webinar, you will receive an email from us thanking you for participating, asking for feedback. And if you want to get the credit, you'll also see there that there is a link to go take a test. You have to click on the link, take the test, and you have to pass it with 70%. And then we then report that to RCEP, and then you get your credits through their website. So this just means that we're consistent with their standards and requirements. This does not mean that they endorse or approve anything that I say today. Purpose statement. So we're going to talk about lightning. So the nature of a lightning strike, talk about frequency and intensity. In particular, the emphasis today is going to be, I'm trying to make this practical for transmission line design engineers. I think there's something for everybody here, but in particular, my target audience is transmission line engineers who have to really deal with this. So I'm trying to make that useful for them. Let's talk about lightning class levels, and then at the end, we'll close with how you deal with lightning damage. So again, trying to be useful for you guys. Here are some specific learning objectives, and I'm not going to read them to you. I'm just going to give a couple minutes and pause and let you look at them. So you'll see more details about what I'm expecting that you'll learn out of this class. Okay. Hopefully you got all of that. So here's the webinar rules and the flow for today. So this constitutes the introduction and sound check. The actual presentation should last about 75 minutes. And after that, we'll have Q&A. So today, we're using MS Teams, and they don't have a separate Q&A feature in Teams. So we'll use chat. So please save questions for the end. But during the presentation, it's okay to type the questions into chat. It's just I won't respond to them until the end. And if I need to go back to a slide or something to answer a question, I'll do that. No problem about that. However, no business. That's the NB. So if you've got an order with NCAB in progress or something, please refrain from those types of questions. Let's just talk about general technical questions on this topic, lightning. Now, I say let's start, but before we begin, I want to point out something. The way these webinars go is that I scratch something out on a back of a napkin kind of thing, and then I turn it over to our marketing people, and then they polish it up and make it look presentable. And this time I got the comment, hey, Mike, a lot of these slides, they have a lot of information on them. It's too much. We need to simplify it. And my response was, no, okay, this is Engineering 401. So that's not just a name, that's a concept. So this webinar is not for the faint of heart. We're not freshmen here. We're not children feeding on milk, right? We are seasoned professionals, veterans, you might say, seniors, about to graduate. So this has hard hitting, dense content, not for the faint of heart. So just keep that in mind. Okay, First, we got to do a quick review to orient you. So really, one aspect of this, being an advanced level class is it assumes that you already have a basic understanding of OPGW. That's an important underlying concept to this, that you already understand the basics of OPGW, and then that was a OPGW 101 seminar that we do periodically. We've done it a couple times now, I think. But I need to make sure that you're oriented. So this is kind of a quick refresher. There are three types of OPGW used today, and you'll see how this is relevant later. Center tube types, which have two flavors. So you have a center tube, which is a stainless steel tube that could either be plain, like you see in this one, or it could be in an aluminum pipe or covered, meaning clad with aluminum, like you see in this illustration. So that's center tube types. Then you've got aluminum pipe type, which has an aluminum pipe. It could be made from extrusion or welded, but it's basically a relatively thick wall aluminum pipe. And inside you have plastic buffer tubes, typically stranded around something. In this illustration, an FRP center member, fiberglass reinforced plastic center members. And then last but not least is the stranded stainless steel loose tube type design. And that's what you see in this illustration. Might have one tube, could have typically two or three tubes, could have in some designs even up to six. So we'll talk about these later. Okay, again, more in the kind of reorienting everybody. OPGW, the primary function of OPGW is to replace a conventional shield wire, and that means that it has two primary functions. To protect the phase conductor from lightning is one of them, and hence that's the reason for this webinar. This is one of the most important functions of OPGW. And then the secondary, it adds a path, So the primary function, the second primary function is to provide a path of fault current. And then the secondary function of OPGW was to add optical fiber for data and communications. Now, some would argue that in our time, the secondary function is perhaps actually more important to a lot of people than the primary function, but nevertheless, this is really the way it ought to be looked at. And it's been around since the late 80s. So why is lightning performance important? Well, look at this. The UTC did a survey of its members some years ago and then published a paper by Mike Unser of Salt River Project and Dan Newman of Burns and McDonald in 2017 at the UTC National Conference. And it showed that the results of the survey was that the second leading cause of OPGW failure was lightning strike. Close behind problems immediately after installation. So really, during long-term operations, you could even argue that lightning was the number one problem, and by a hefty margin compared to the others. So it's an important topic, and I kind of felt like it doesn't get the attention it deserves, given its importance, and given the fact that lightning is one of the primary functions of lightning protection is one of the primary functions of OPGW, and hence this webinar. So let's get into lightning. First, let's talk about what a lightning strike actually is. We see the flashes of light at night and they're, quite quick. It turns out that there's actually a lot more to a lightning strike than you might think just from observing them when there's thunderstorms in your area. There's actually four components. The first is an initial strike. That's this component A. The second is an intermediate current. That's this component B, which is like a transition from the initial, like you could call it a pulse, the initial strike, to a continuing current. That's this component C. And then there's a restrike, which is another impulse like, and this is a component D. Now, it turns out, for reasons which we're going to explain on the next slide, we know that this continuing current component is actually what damages cables. So, to understand why that is the case, you kind of got to look at the wave component in more detail and factor in that this drawing is not to scale. So first, the amplitudes, you can understand I've got pulses here. Those are on the order of kiloamps. And of course, that sounds like a lot. Like you would expect that that would do damage. 200 kiloamps is typical. Peak amplitude on the restrike is 100 kiloamps, and that's not anything to sneeze about. The continuing current is around 2 kiloamps. Again, still not, that in terms of sheer number, that's a lot of current going on. And then the component C, the continuing current component, the amplitude is on the order of hundreds of amps. It shows here 200 to 800 amps. So, why are we worried about something that's only a few hundred amps and not the things that are kiloamps? And the reason for that has to do with the durations that you see down here. So that initial stroke is on the order of microseconds, and uh, the intermediate current is on the order of milliseconds. The continuing current is on the order of seconds, and then you're back to microseconds again for the restrike. So if you integrate across this waveform and look at the energy that's in each of these components, and by the way, I simplify this C, here's what you get. The A component has 50 amp seconds, right? Because amplitude is in amperes, and on the y-axis, the x-axis is on seconds. So if you integrate it, you're getting the area, and that gets you amp seconds. And we define 1 amp second equals 1 coulomb. And this is often referred to as charge transfer. So 50 amp seconds. The B component, the intermediate current, is 10 coulombs. And the C component is 300 if you simplify the waveform the way I talked about. And the D component is about half of the initial strike, 24. So you see A, B, and D are all on the order of 10 in terms of magnitude. C is on the order of hundreds. So it's an order of magnitude greater energy, and that's what's doing your damage. And it's important that you remember coulombs as a concept as we continue through this presentation. So what's the source of lightning? Well, obviously the clouds. You can get some information about isochronic level, and we'll talk about isochronic in just a minute in detail. You can get an isochronic level map that shows you the number of flashes that occur in your area each year. You can find these maps on the internet. Well, I'll talk about it in a minute. And it's true that the cloud to ground flash density does correlate with the likelihood of lightning damage, right? Because if I have more strikes in an area over here in Florida, say, than I do in, say, the state of Washington, well, I would expect more damage in Florida than in the state of Washington. That's true, but it's not really complete, and it's not really fully useful at that point because you're missing information about duration and intensity. Coronic level itself, and it's sometimes spelled differently, means the average number of days per year with lightning being detected. And as I mentioned, you can find these maps for anywhere in the world, basically. The biggest source is this company called Vaisala. They're out of Finland, but they do charge a fee. Now, when I was preparing for this, I thought, well, I could just go to the National Weather Service which I did not realize was actually part of the NOAA, the National Oceanic and Atmospheric Administration. And I thought I could get data for the US, but it was funny to me that it referred me back to Vaisala. So I figure there must be big money in getting and selling lightning data, which was a little bit surprising to me. But anyway, originally these maps were obtained by collecting data from the sound of thunder. And then like in the 70s, you begin to get electronic detection using radio wave disruption. And now it's done by satellite using a technique called, or a technology called, near infrared detection. So that's some background on lightning. And I said that this presentation is intended to be practical for transmission line designers. So if you're a transmission line designer and you're concerned about lightning at your utility, what have you got available to work with? Well, you got 4 resources available to you. There's your utilities experience, there's studies, there's the standards for OPGW, and in particular, the laboratory testing that's incorporated in those standards. And then you've got the cable manufacturers themselves, and we're going to talk about each. So up first is what can you get from the direct experience of your utility? And the first thing to think about is what's been going on with your conventional cables, right? Because before OPGW came on the scene in the late 1980s, as we mentioned at one of the opening slides, utilities have been operating for decades, and they had used cables like 3/8 inch HS or EHS and 7 number whatever ACS cables. So what was the experience there? Did y'all have a lot of lightning damage? If so, how frequent was it? How bad was it? Was it calling cables to outright fail, or was it strand damage that could be repaired? It's a background to start from. Now, since OPGW has been on the scene now for over 30 years, your utility probably has experience with OPGW. So what's its track record? Similar to how we talked about the track record of the conventional cables. So use the actual direct experience to inform what you decide to do as we continue to talk about what options you have available. As I say, apply the lessons learned from either or both. And if you're having problems with damage, then you have to face the truth, right? There's an old saying that insanity is doing the same thing over and over again and expecting a different result. So if you're having damage and you're just putting up the same cable and hoping that you don't have any more lightning damage, sorry, that's shades of that definition of insanity. You need to change something. But then the question comes up, well, what should you change it to? Hold on, we'll keep talking about things like that. And in the rare case that your utility has actually collected data on the frequency or intensity of lightning in your service area, so not just the isochronic information, but the intensity of the lightning in your service area, how strong were the strokes? You need to take advantage of that. So the second resource that you had was insight from professional studies. And unfortunately, I got to tell you, this was a little bit disappointing, you may find. Ideally, you would find studies with detailed information, not just the isochronic level, but about the severity of lightning in your area. So stroke intensity, that's a factor, and stroke duration. Right? Because remember, when we integrated, we were looking at the intensity, the amplitude of the lightning, and the duration of it. But you don't find that data. And what you find actually is contradictory. Some published data suggests that negative polarity strikes are more frequent in the field and that they're more damaging. But other data suggests there's no difference in damage between positive polarity versus negative polarity strikes. So unfortunately, You don't find a lot of help from studies at this point, but of course we can be hopeful that in the future there will be more data available. More data and more useful data, I should say. So your third resource were the standards. And so we're going to talk a little bit about the standards. What can you learn from the standards? The two most commonly used in the world are IEEE 1138. The 2009 edition is still in effect, but there is a revision that's coming out real darn soon. It's been voted out of committee already, but it's got to go through some additional processes within the IEEE organization to get approved and officially released. My best guess is I think that will happen this year. And then there's the IEC standard. A rough rule, and it's a very rough rule, is we see the IEEE 1138 applied in the United States, and in most of the rest of the world, we see the IEC standard. They're very similar, though, but they do have some important differences, especially when it comes to lightning, and we're going to talk about that. To understand and put the standards in context, you need to understand how they evolved through the years. So in the 1990s, it was still the early days of OPGW, and there wasn't a standard for lightning or lightning testing until the IEC included it in their standard in 1999. Prior to that, so you had about a decade where some manufacturers or utilities were doing kind of ad hoc lightning tests. Those generally took the form of an impulse test. So basically component A. So you would subject a cable to a pulse like 50 kiloamps or 100 kiloamps. I really don't think that too many of them went up to the 200 that you saw on the previous slide. And few, if any, cables failed because that A component doesn't do a lot of damage. The pass-fail criteria was also very subjective and very, meaning unclear. You know, it was a standard such as no significant damage. Well, but what does that really mean? So there was a recognition that something needed to be better. We needed something standardized and more useful than what was being done in these ad hoc tests. And we also needed a verification that testing needed to have like a connection to what was really going on in the field. And as we saw already, if you're just doing impulse tests, you're not at all being realistic compared to what is going on in the field. So I got this information from Connectrix. This shows the evolution of the IEC standard. And in its current form, the testing is based only on the continuing current using positive polarity, and you check how much strength is left in the cable. So let's look at that. By the way, in their standard, when they began in 1999, they did use that 4-component waveform. So there was already a recognition that impulse tests weren't cutting it, and that what you really needed to focus on was that continuous current component. So in more details about the standard, the IEC standard, you have 5 simulated strikes, which we generally call hits, with positive polarity. Remember, there was this debate about is positive or negative polarity more damaging. You're focusing only on the continuous current component. And you have a pass-fail criteria based on calculating the cable's remaining strength after the 5 simulated strikes. And you do that by excluding broken wires. That criteria is that calculated remaining strength must be greater than 75% of the rated breaking strength of the cable. The obvious question that you can draw from this is this really accurate? Because what about those wires that might just be burnt or damaged? Or what about the possibility that the steel or the aluminum alloy in the cable has lost strength due to annealing? Well, the truth is you don't know, and you're just sort of ignoring it. Here was the evolution of the IEEE 1138 standard. And you end up in a similar place, but with some significant differences. In the IEEE standard, you do those 5 hits with negative polarity, but you're still focusing on the continuous current component. And you have a very similar pass-fail criteria, except that you're actually testing the cable's remaining strength. So after the 5 hits, you take the cable and put it in a tensile testing machine and you pull it till it breaks. In the 2009 version of the standard, it had to be greater than 75% rated breaking strength. Same as the IEC. The thinking within the IEEE organization was that 60% rated breaking strength, so 60% RBS, was the traditional limit within NESC, the National Electric Safety Code of the United States, Rule 250B. So that was the maximum limit under this rule. And then you had 15% as a margin for error. However, what wasn't known when this was adopted was that the smaller, the center tube type designs that we focused on one of the early slides, or recall those designs tend to fail. And we'll explain why later. So in the new version, because of this, it was decided, well, maybe this is being too conservative. And these cables do have a real role in the field. You know, I talk about that in the OPGW Engineering 101. So it's not that they're bad cables. They just tend to not pass this test. And so 75% rated breaking strength is going to be replaced with the remaining strength must be greater than the maximum rated design tension, MRDT. So that's the maximum tension that the cable is supposed to experience during any of its ice or wind loading conditions. So smaller center tube designs, their MRDT typically is in the range of 40 to 60% rated breaking strength. Might be a little bit lower for some cables. Rarely is it any higher than this. So now you can see effectively you've lowered this requirement to being 40 to 60% for these cables only. Other design types may still have a higher MRDT, and therefore they have to meet their manufacturer stated MRDT. The standards, both the IEC and the IEEE, added the concept of lightning class levels. And a class level is intended to be a standardized severity level based on that charge transfer in coulombs. And the reason for that is that allows you to compare and contrast test results. So you can get a relative comparison between 2 or more cable designs. So you can directly compare 2 designs, design A compared to design B. Now, that doesn't necessarily mean that design A is better than design B in some categorical all across the board sense. It just means on this test, design A might do better than design B. Don't overgeneralize. You can also compare different design types, right? Center tubes, aluminum pipe, or the stranded stainless steel loose tubes. So for example, you at a utility could have a list of requirements, and maybe you want to compare the performance of a center tube versus an aluminum pipe type design. You can do that. And maybe based on your specifications, one manufacturer might quote a center tube design and another one might offer you an aluminum pipe. Well, if you've done the test, then you can compare the performance of the two. You can also compare different manufacturers in theory, but really this is a function of the design differences, I think. Right? Again, if you're specified a certain diameter and a certain fault current and a certain strength and whatnot, and a certain fiber count too, of course, manufacturer A might quote center tube and manufacturer B might quote aluminum pipe. So if you then compare the the test results, there might be a difference, but it might be a difference related to the design type and the design differences as opposed to manufacturer A is better than manufacturer B. However, it is possible that optical differences might show up in such testing because the lightning test is not directly saying anything about, and the pass-fail criteria is not necessarily saying anything about the optical unit design. So one manufacturer might be a little bit more conservative, shall we say, in their design for excess fiber length. Remember that concept that comes up, or the zero fiber strain margin, another concept that I'm expecting you to already have some idea what it is, than another manufacturer. And so that could show up in testing. And strictly speaking, the lightning results might be exactly the same in terms of maybe number of wires broken and remaining strength. Manufacturer A and manufacturer B could have exactly the same outcome, and yet the optical differences could be quite different. So that could show up. And again, or the last benefit of applying these lightning class levels is verification. So you can use the test results to verify that what you have specified is met. Okay, what are those class levels? Well, there are 4: class 0, 1, 2, 3. Class 0 is the easiest. I hate to say it that way, but that's the word that popped into my mind. So you have 100 amps, half a second. You'll see they're all half a second. So your total charge transfer is 50 coulombs. Class 1, it's 100. Class 2, 150. And class 3, 200. So this is the most severe. So the obvious question from presenting these classes is, which one should you use? Well, hold that thought for later. We'll come back to it. Just to give you some more insight as to how this testing is done, this is a typical setup. Again, I appreciate that I was able to get some information from Connectrix. Basically, the cable is under tension to simulate like an everyday condition. And then you place an arc head, typically within 1 to 2 centimeters of the cable, and you generate an arc across the gap. Usually there's a fuse wire to get it started. That burns away, and then that leaves you with an arc. That's, the simulation of a lightning strike. Then you have your equipment to monitor the optics during this. Just a very typical setup here. Now, I mentioned that the IEC, you calculate the remaining strength, and the IEEE, you measure it. And we'll talk about these in more detail. For now, what I would like to show is that if your testing is per the IEC standard, you then have to take those cables that you hit and put them in a tensile testing machine here's a typical one, and pull on it until the cable breaks. The cable typically breaks, no surprise, where it was damaged by the lightning strike, simulated lightning strike, I should say. And then you apply your acceptance criteria. So in the IEC standard, it's a calculation, and I've already said you ignore burnt wires that are damaged. And so as a consequence, those wires are not factoring into that calculated remaining strength. And I think that's important to at least be aware of. The IEEE standard, you're measuring the remaining strength by tension testing, and consequently those burnt or damaged wires, they do reduce what the actual remaining strength is. This is best illustrated by showing you a case study. In this testing, which again done by Connectrix, a center tube type design has a single outer layer of 8 aluminum clad steel wires. The test broke 0 wires, but it damaged 3. You see that in the picture here. 1, 2, 3. And if you look closely, I kind of wonder if there's not some damage down here, but let's take it at face value, 1, 2, 3. So Using the calculated acceptance criteria, you have no broken wires, so you have 100% remaining breaking strength, RBS, or rated tensile strength, RTS. So yeah, you met that 75% standard, so that's a clean pass. Woohoo! However, when you actually went and did a tensile test, you still had no broken wires, but when you measured the remaining strength, you got only 70% rated breaking strength, and that's less than the 75% pass-fail criteria, so therefore that's a fail. So which is it? Did the cable really pass, or did the cable really fail? Another example of what you can get from actual testing. So here's the same cable tested to 2 class levels. You really do see a difference. So here, class 1, 100 coulombs, the cable had close to 80% remaining strength left. But if I went up to class 3, 200 coulombs, I had 54% left. Likely a clear failure. Of course, it depends, what your criteria was. But per the IEC standard, absolutely a failure. Per the new IEEE standard, maybe it's a pass. Don't know. So I think, isn't it intuitively obvious that you should be using the measured criteria? You could even be applying the IEC standard and say, I want the testing per the IEC standard, but I want the actual remaining strength tested, and I would be fine with that. But you should just understand trade-offs. This does add cost and time to a test that's already expensive. So a basic lightning test at a good quality lab like Connectrix is on the order of about 25 grand. You also have to understand that some labs around the world, so if you went to your closest lab, they might be able to do the electrical test, but not do the mechanical one. And of course, there are labs that it's the opposite. They can do mechanical testing, but they can't do the electrical testing. So you do have to be aware of that. Some of you might have thought, well, can't you improve the calculated criterion by treating those burnt or damaged wires as if they are broken? And my conclusion is that doesn't help, right? You just get a third answer. If I applied this concept to the test case here, then you get 63% remaining breaking strength, right? If you neglect the strength of the tube. So, okay, now what? Again, is it a pass or is it a fail? So, that's useful information about the testing, but how can you actually apply it? And so what I'm going to do is go through what ideally a transmission line engineer could do. So first you would begin with taking those lightning class levels and determining the rating for your OPGW. So, for your utility. Okay, well, how do you do that? I've got this isochronic level, but Mike, you already told me its intensity and duration is important, and it's really that charge transfer that's important. How do I get that data? Well, sorry, you've kind of got what I call here scientific sorcery or swag, scientific wild guess, or just plain guesstimate. So you kind of got to guess. Now, the isochronic level can put it in the ballpark. As I talked about before, if you're in Florida, you know that you have more intensity than if you're in the state of Washington. Or maybe not intensity, but you definitely got more concern in the state of Florida than you do in the state of Washington. Now, you could look at this graphic and the legend, and as an example, this is totally arbitrary. I don't want one person who attends this webinar to go out and say, well, Mike Riddle said that class 0 should be 0 to 8 on the isochronic map. I did not say that. I just said it's got 1, 2, 3, 4, 5, 6, 7, 8. So that means if I use 2 I get a nice clean mapping to the classes. It's totally arbitrary. I did not say, do it this way, just an example. You could adjust up or down based upon the experience that your utility is getting, right? So, but anyway, it does map nicely. Class 0, 0 to 8, class 1, 8 to 16. You see how I did it here. But let's say that you're in an area and using this totally arbitrary criteria that Mike Riddle did not recommend applying this way. But nevertheless, if you did, you might say, well, class 1 looks appropriate, but we're actually having damage. So maybe we up it to class 2. Or the reverse could be true. Looks like it ought to be class 1, but we're going to have a lot of damage. You could drop it to class 0. Make some adjustment, but this is half science and half sorcery, as say here. Okay. Then, after picking your class level, do the testing. Does your cable pass the level you pick? Now, even if that's a yes, you should also consider the coordination with your sag and tension requirements as you do them at your utility. So is the remaining strength really adequate for your utility? Ideally, you want to avoid a complete catastrophic cable failure in the field, right? Right? You don't want cables just falling down. So if the cable's MRDT is less than 60% rated breaking strength, is this okay? Step 4, is any field data available to help you put the results in context? So you could compare what you get out of laboratory testing to what you actually get from the field. So if what I mean by that is maybe in the lab test, consistently 4 or 5 wires break. But then when you have reports of damage in the field, it's only 2 or 3 wires are broken. Well, then maybe you can drop a class level. And it is my own observation that lab damage does seem to be more severe than actual damage reports from the field most of the time, but not always, because I have seen cases of cables that completely failed in the field as a direct consequence of lightning damage to them. So the kind of like I'm coming around to saying about the best you can do in this situation is apply risk management type techniques to come up with an answer that works most of the time. So if you don't have data available, maybe you can suggest at your utility that you guys start keeping track of that. When there is damage in the field, get the lineman to report it and somebody collect it and organize it and analyze it and then apply it to your cable design in the form of adjusting your specifications and iterate if necessary, right? So if it's not working, right, if you make a change and it's not working, then change back to what you were doing before or change to something else yet again. You also need to understand that improving lightning performance comes with trade-offs relative to other design considerations. I'll talk about this more in a minute. So let's hold that thought for a moment. But the concept here is that those trade-offs, what I mean is that if you need better lightning performance, you're likely making your cable bigger. I mean, flat out, in some fashion, more metal is going to give a cable better ability to withstand the lightning energy and dissipate it. So more metal means somehow the cable is bigger, heavier, and in turn, bigger, heavier means cost goes up. Other considerations. So you may decide, again, applying risk management concept, that you just need to change your expectations, right? That the level of damage that you're having now is such that it doesn't justify the economic trade-off that you would encounter by substantially trying to improve your lightning performance. So resource number 4 is what you can learn from OPGW manufacturers themselves. Everybody has had strikes on their cable, whether it's in the field or the lab. Maybe not all of them from the field are reported to them, but probably some are, and they certainly have lab results. So all of them have had damage to their cable. So what have they learned from that? So you should filter and compare and challenge when it seems appropriate. What do I mean by that? Well, manufacturer A says, my cable, it's, got 2 millimeter wires. It's the greatest lightning performance in the world. And another vendor says, well, my cable's got 3 millimeter wires on the outside, and I think it's probably still a class 0 cable. Well, you need to challenge manufacturer A to prove his case. Back it up with some data. I can only speak to my experience and NCAB's experience, and as a little bit of a joke here, can you trust those other guys anyway? Trust me, trust me. Okay, anyway, so our experience, rooted in 25 years of experience that I've had in this industry with optical ground wire. General guideline number one. In my view, risk management says that if you design well, and that's an important qualifier, well for your fault current, then you're also going to get good lightning performance out of the cable as a free bonus. A lot of utilities, though, don't design well for their fault current. Fault current is discussed in detail in the OPGW Engineering 101 class. I'm not going to discuss it today. Just that caveat is important. You got to design for your fault current, but you got to do it well, not just, well, we've been using 3S EHS, so let's just make it the same. That's what I mean. That's not designing well for fault current. That's, in fact, in Engineering 101, that's kind of a cop out. You really got to think about it. And again, remember, in this class, we are all supposed to be seasoned professionals. So we darn tootin' true that we're going to design well for our fault current. General guideline number two is that there isn't any other general guidelines. There's no agreement on what to do. Should my wire size be this or my wire count be that? Nobody would agree. And I know that for a fact because in the IEEE committee meetings for the subcommittee that's responsible for the IEEE standard, there have been those kinds of debates, almost coming to fisticuffs between people over these kinds of issues. Nevertheless, I can offer you 5 observations that I think are helpful. First observation is that size matters. All else being equal, a larger wire or a larger overall cable diameter seem to perform better in the field. So as a consequence of this, what the larger wire means is that a larger wire is less likely to be burned through than a smaller one. And as a consequence, I see some utilities have adopted minimum wire sizes. Do I think that's necessary? No, I don't, because go back to what I said before. If you design well for fault current, I think you get good lightning performance as a free bonus. Nevertheless, some utilities do have minimum wire sizes. Obviously, as a cable designer and a cable supplier, we respect them. The two most common are either just picking 2.9 or 3.0 millimeters. I mean, those are the ones I commonly see. But generally, when I see nice, clean values like this, I know that they're arbitrarily chosen. There's no real data or scientific basis for this. It just sounds good. Maybe they got some designs from different manufacturers and picked one, the size of their outer wires or whatever, but there's no basis for this. These I don't really care for. Another approach that's taken is to cite your field experience, and that makes sense to me. I talked about that before. So for example, one large utility here in the United States, they said, well, for decades, we used 7 number 8 ACS all over our system. We didn't have a lot of incidents of lightning damage. So we're going to say that the outer wires on our OPGW have to be at least 3.26 millimeters, because that's what number 8 works out to be. And I respect that. I don't think it's necessary, but I respect that because it's rooted in some actual experience, which is to say it's rooted in some real data. But there are the trade-offs. When you do this, this is a relatively large wire size, and it gets you a relatively large cable. That utility's OPGW is 16.4 millimeters overall, which is 0.646 inches, which is a relatively large and relatively heavy OPGW, so it costs more. Now, me as a cable supplier, I don't mind that. I like a nice, big, expensive cable. Looks nice running on our equipment, and my finance people tell me how much money we make making it, and that makes me happy. But you as the user need to understand that you have accepted that trade-off. The larger cable, in addition to costing more, it's also putting more loads on your towers, right? So they may have to be beefier, which means those cost more. It may also decrease your maximum reel length, which could mean more poles and more splices. And of course, that means more labor and more material, right? More splice cans, more storage racks, bullet resistant canisters and whatnot. So all of that's going to cost your utility more money. So do consider these trade-offs before you make a decision about saying, well, I have to have a minimum wire size like this. But again, I respect the reasoning behind this. The overall cable diameter. What I think is going on is that the larger diameter is spreading the strike energy out over a large area. And this comes from some testing. We observed that an AP type cable, so for us, that's that aluminum pipe type design, with a larger ID, but it had relatively smaller wires on the outside. Fewer of those wires broke than a different cable that was a type CA, so the center tube design, which had a smaller OD but much larger outer wires. So the outer wires were bigger on this cable than this cable, but this cable had fewer broken wires. Interesting. So that does seem to kind of contradict this a little bit. And it does contradict it a little bit. But what it's saying is that there's more going on here than just one simple rule or one simple answer. So again, size does seem to matter. It does play a role. That is a fact, but then you can debate the specifics. Observation number 2, material matters. So in general, ACS seems to do better than AY, but galvanized would be better still. However, galvanized you never see used in OPGW because its electrical characteristics are so crappy. As a consequence, some utilities, the consequence of material matters, some utilities do require an all ACS outer layer. That same utility that I talked about here, they require an all ACS outer layer. So they require the outer layer is 3.26 millimeter and all ACS. That makes that cable substantially heavier and stronger. And so all else being equal, it costs more. So again, remember those trade-offs again. And then this thing also brings in, another wrinkle. You draw some conclusions, and then Mother Nature kind of laughs at you sometimes, right? So yeah, the material matters and the size matters. Well, there was another thing in that testing, the AP cable, so the aluminum pipe type cable with the larger OD and the smaller outer wires, those outer wires were mixed, and yet none of them, including the aluminum alloy wire, were broken, or fewer of them were broken. But actually what I remember was there were no aluminum alloy wires broken. Then the center tube design that had a smaller OD but larger outer wires that were all ACS. And it seems to contradict what the observation here is in general in this specific case. So what you can think from these two observations is that there's actually a third thing going on, and that's that wire count matters. Because the cable with the larger OD and the smaller wires had a higher wire count. And the basis, the fundamental issue or the underlying issue that's going on there is that X amount of energy, coulombs again, will burn Y wires. So if there's 12 wires, Y of 12 gives you a lower reduction in strength than Y of 8, right? So let's keep it simple. Let's say that Y is 1. So a certain amount of coulombs is applied and it burns 1 wire. Well, if there are 12 wires on the outside of a cable, 1 out of 12 is a lower strength reduction than 1 out of 8. 1 out of 8, what you've lost around 12% of your strength. And the testing that we talked about on the previous 2 slides, it's consistent with that. So it could be that this is actually the most important variable, followed by maybe material and maybe sizes. Maybe this is important, but not so much this. Hard to say. Observation number 4, design type is a factor too. And the center tube designs, there's nothing wrong with them. They are not bad designs. From a lightning standpoint, they do good. We don't see center tube cables falling down all around the country or the world. They do good. But when you do the laboratory testing, they do seem to have more damage. That's consistent with the testing that I've been talking about here and just in general. So if I was to rate it, I think they're good, but I think the aluminum pipe type designs do a little bit better. And the ones that do the best, I think, are the stranded stainless steel loose tube designs. But again, remember the trade-offs in size, weight, and cost. So I kind of think that what I just said is true, that probably wire count is really a major consideration, plus maybe the overall ID, and then that the material comes into play, and then maybe it's the wire size itself is last. But they all do have an effect. And then the last observation has nothing to do with the cable design itself, and it's this. It's that low footing resistance correlates with low incidence of lightning damage. In this presentation, I've talked about Florida a lot, not just because I like the state of Florida, but I do. But they have a lot of lightning there, but they don't have a lot of damage. And one of the things I've learned over the years is that the utilities there do a good job of making sure that they have low footing resistance. So at the bottom of the towers, they're making sure that they're grounding them and grounding them quite well. And they don't have a lot of damage from lightning. Well, why is that? Well, I think it has to do with the fact that the strikes are more likely to hit on or near a structure if you have good grounding. If you dust off your old EPRI Red Book, you'd see buried in there that 75% of strikes hit at or near the structure. And if you're hitting at the structure, it means that the cable is not being hit. And near the structure, right, if it hits the structure itself, near the structure means that the strike might hit on the supporting accessories. So both dead ends and suspensions have greater metal mass, and that mass acts to dissipate the energy better than the cable alone can. Armor rods that are used with dead ends and suspensions also tend to have a larger diameter than the cable wires themselves. And so again, you have this size effect coupled with more metal to dissipate that energy. And by the way, this does assume low footing resistant, that the accessories themselves are well grounded. And so what you're doing here by paying attention to your footing resistance is you're creating conditions that push the odds in your favor. If you have 100 strokes, and let's just say, to keep the math simple, that 10% of them are going to damage your OPGW. So if you have no footing resistance, what you might do is shift these odds to be 50-50. So 50% hit the structure, 50% hit the cable. So if 10% of them are going to damage the cable, then those 50% that hit the cable, you would expect 5 good footing resistance and get 75% hit at or near the structure. Let's assume no damage from those. Now I've got 25 strikes that hit the cable, 10% do damage. I've cut my incidence of OPGW cable damage in half to 2.5. So you're pushing the odds in your favor if you pay attention to this. Now, no matter what you do, how well you've designed your cable and specified your class levels and all those other things that we've talked about, it's going to eventually happen. As I mentioned earlier, Mother Nature sometimes laughs at us mere mortals. So what are you going to do? When you have damage, basically you've got to either repair it or replace the cable. And we'll talk about both, starting with repair. Repair rods, which basically are a specialized set of armor rods. So they're grit in the rods, restraining electrical conductivity in addition to strength, dissipate, or from additional lightning strikes in the future. So if the optics are working fine, so if you have an incident of damage, the first thing you should ask yourself, likely if your communication people didn't report anything wrong, they probably are, but you may need to go out and actually do an OTDR test to verify that the optics are fine. And if they are, then the repair rods might be an option. There are guidelines for them. In general, you need to have 50% of the rated remaining strength of the cable. And you have to confirm what the specific guidelines are with the accessory supplier. So whoever makes these rods have to tell you what their rules are. Are on hand. The disadvantages are you got to work with your supplier to get an estimated strength, and there is possible error in that for all the reasons we talked about before. There can be a hassle factor of installing, right? It's easy if you've got some damage, I don't know, 6 inches off the dead end close to a structure. It's hard if it's at the middle of a span that's 2,000 feet long. That's crossing in. There's more involved in the second situation. So there is that. Of course, it's still probably a lot easier than replacing the cable. And of course, you got to source or stock these repair rods. Replacement. So in some cases, you're not going to be able to repair it. Obviously, if the cable's already lying on the ground, you can't repair it. So what are you going to do? The big problem with replacement is that becomes a crisis because of the time, right? Because OPGW standard lead time is 10 to 12 weeks ARO after receipt of order. So you do have some workarounds. If you don't have cable immediately available, one of the workarounds is that you could use ADSS or some kind of a dielectric cable as a temporary repair. Advantages, that can be done with the line still energized. So the phase conductors can still be operated while you're making this repair, and it's a pretty quick and easy repair most of the time. Again, maybe some situations it would be more difficult, but in general, it can be done pretty quickly. Of course, the disadvantages is you're doing extra work because you're putting in a temporary repair and then you got to go back and do something permanent. You're doing like a temporary replacement and then you got to come back and make your permanent replacement. That ADSS cable might be relatively vulnerable during the time when it's up as a temporary repair, or if you use dielectric cable, like I'm talking literally, you might lay dielectric cable on the ground from structure to structure, but that would make it vulnerable, but you could get away with that for a short time. And you've got to source this cable that you're working with and maybe the associated accessories for it, like if you're using ADSS literally as an aerial cable. So workaround number one. Workaround number two is to keep an emergency length of cable on hand. It should be on a steel reel. Now, most cable manufacturers, the steel reels are supposed to be returnable, and they want them back in 3 months or 6 months or a year or whatever. So, you have to tell them, yeah, I need to buy this one. But they'll use, I would expect any cable manufacturer is going to say, okay, and it's just a question of, yeah, we we want you to pay us X because you're not going to return our steel reel to us because steel reels are kind of expensive. So an emergency length of cable plus the accessories, right? My suggestion, get what you need, put it in a sealed crate. Then when you have an emergency, the replacement can be done quickly. It's permanent, and there's no scrambling to obtain cable and accessories. But of course, you have to keep track of where your kit is. Disadvantages is you got to source all this stuff up front, and meaning pay for it, and you got to maintain the kit. There's a national, I would seal the kit because there's a natural tendency for people to borrow it, right? Oh yeah, you got to open your emergency kit and find, hey, there's no dead ends in here anymore. I know they were here before, and then some lineman tells you, oh yeah, we were short on that project last year, and we borrowed a couple and kind of forgot about it. So you got to be cognizant of that and plan accordingly. And of course, you got to figure out the quantities. How much is enough? Do I need 2 dead ends or 20 dead ends? But you think it through. You can work with the cable manufacturer and your accessory vendor, and I think you can come up with something that's appropriate for your utility. Another tip about reusing the existing hardware, it is okay to reuse tangents, but in general, it's not a good idea to reuse dead ends. They really should be new. Now, if you absolutely had no other choice, yeah, okay. Maybe temporarily, okay. But in general, it's a better idea to use brand new dead ends. If you're replacing, how much do you replace? So you could just replace the affected span, right? Maybe this structure, that structure, a span of 500 feet. If you do that, you're adding 2 splice points. But you're not, you're in that particular case, you're only using 2 dead ends and only 500 feet of cable. So that's, that makes it less expensive. From a cable standpoint, the splicing points, that may tilt the equation a little bit. In general, you don't like adding splices unless you have to, but in these days, the typical splice loss at 1550 is about 0.01 dB, and the maximum is less than 0.05 dB. So even if guy did a not so good job splicing, you just say, well, do it again. It won't take long. You could probably specify that the maximum allowable not be more than 0.02 dB. And that would be a reasonable way of giving some latitude for reality in the field. But the main point I'm trying to make here is this is not overwhelmingly going to adversely affect the optical performance of the system. It's okay. You could do span to closest splice enclosure, right? So from the affected point, let's say it's in the middle of a segment that's 10,000 feet long. And I said in the middle, but let's say there's a segment, it's 10,000 feet long and the damage is at 2,000 feet from one end of that segment. Well, then you could do 2,000 feet back to that closest tower and only replace that 2,000 feet. Instead of all 10,000 feet. That would add just 1 splice point instead of 2, but it obviously then requires more cable, 2,000 feet of cable versus say 500 feet of cable for illustrative purposes. So in that hypothetical example, you have the damage, it's 2,000 feet in from a 10,000 foot segment. You could replace the entire segment if you wanted to. So we're coming to the end now. Here's a quick recap. Yes, utility lighting performance needs based on your experience to date. We've talked about direct experience. We've talked about the studies, which I admit don't really help a whole lot. The standards. And suppliers. So really your experience, insurance and suppliers, those are your main resources available to you. And you'll decide if your utility specification should include lightning class level or some other requirement, right? The all ACS outer wire requirement. Then you should test to confirm that your OPGW is meeting your requirements, and you should adjust your specifications accordingly based upon what you learned from the testing. And then again, no matter how good you do on all of this, Mother Nature will laugh at you and throw a bigger lightning strike at you and damage some cables. So you need to prepare for the eventuality of lightning damage. You need to at least think it through what you'll do if or when that actually happens. And that concludes the formal part of the presentation. Let's go to chat. And if there are questions, you should submit them in chat. If I can find chat, here we go, chat. So got to go back to the top. So question, Joseph from Mid-American. In the West, we are experiencing more and more wildfire burn-throughs. Are there any standards or testing that pertains to heat resistance and the ability to survive wildfire? The answer is no. That's not been even contemplated by at least the IEEE subcommittee that I sit on, and that's a darn good point. And Joseph, I would appreciate it if you could prod my memory by sending me an email about that, and I will bring that to the attention of the committee, and maybe we do need to think about that. Again, because you could be in the situation where it's easy for me to suggest, well, I could do a fire test. Okay, but what are the specifics? How hot is the fire? What's the distance between the fire and the cable? What's the pass-fail criteria? You have to think through all of those things. So that's an excellent question, Joseph. Please reach out to me by email to prod my memory to talk about that with the IEEE. Let's see. I'm not sure. Daniel? In Costa Rica, we are working with T-Flash software of EPRI to determine how many impacts in OPGW we can expect in 1 year of positive and negative lightning strikes. Then estimate the impacts only of the positive ones. They transfer more charge than the negatives. Then we distribute it in a probability function to determine the probability that some positive lightning strikes overcome 200C. The mean is 85C for the positive ones. Proposed that methodology with Vaisala. We built maps for the transmission lines in Costa Rica. And I think that's all great input. Our problem in Costa Rica is that 40% of the downward lightning are positive ones. Around the world, they represent only the 10% approximately. I hand it to you guys in Costa Rica. That's excellent methodology, and I will spend some more time looking at it and understanding it, and maybe I'll incorporate what I learned in this presentation for the next time. Any more questions, please feel free to drop them in. You'll receive a follow-up email from me. If you think of other questions or concerns that you have, feel free to reach out. And again, if you want to get your continuing education credits, be sure to take the test.